Hi guys, my name is Feiyu, and I am currently a PhD student at Virginia Tech. And today is my great honor to be here to present to you our research products during my undergraduate study at Xi'an Jiaotong Liverpool University just a couple months ago. So the title is Evaluating Engagement Level and Analytical Support of Visualizations in VR Environments. Before I begin, I want to deeply thank our team members, Difeng, the proud designer of Visa Text, and our supervisor, Dr. Liang, and Wenjun, Dr. Konstantinos, and Dr. Ali. So first, let me give a brief introduction on to interactive visualization tool and why it is important. Interactive visualization tools are tools to engage users in exploratory, analytical, and sense-making activities by interacting with those visually represented information. So to make it simple, there are tons of concepts or data that are so abstract and complex. We can hardly understand them by just reading a book or just through our own imagination. So interactive visualization tools are specifically designed to assist such tasks using computer-generated visualizations. And users can intuitively learn abstract contents by just interacting and playing with those visualizations of those abstract concepts. And below are two typical examples of interactive visualization tool. The left one is a tool named Molecule, and it is a molecular visualization program developed in the 1990s. And the right one is a recent tool that helps people to understand four-dimensional geometric shapes. When turning these interactive visualization tools into virtual reality environments, computer-generated 3D visualizations can be provided to surround the users in 3D space, and user can see them from different angles, different perspectives, and also user can interact with those 3D visualizations in a way that close to how we would normally interact with real-world objects in the physical world. So there has been some work applying VR to support the exploration of interactive visualizations. For example, the picture on the left is people are using VR headset to support the explorations of scientific data. And also with the proliferation of VR head-mounted displays, interactive visualizations in VR becomes increasingly promising and demanding. So our goal of the research is to evaluate whether immersive VR interactive visualizations can support and engage users in analytical reasoning, exploratory, sense-making, and knowledge acquisition tasks. So to evaluate this, we use 3D geometric shapes as testbed. So we have three kinds of geometry shapes: the cube, octahedron, and tetrahedron. And by truncating, by slicing off the vertices or edges of those shapes, it is possible to obtain a variety of other solids. So such properties are considered hard to learn and explore based on previous researches. And except the intriguing interrelationships among the 3D solids, there are some additional reasons that we are using 3D geometries as testbed. So the first one is 3D geometry is considered fundamental to computer graphics, engineering, mathematics, and architecture. And also for visualizations of abstract contents, for example, molecular structures or scientific data. The structural properties is like the basic structures of a 3D object. And also the transformational properties, it's like how the object can be transformed into another object, is generally considered as crucial to our understanding of these abstract concepts. So thus, by using 3D geometries as a testbed, we hope that our result could be more generalizable to other interactive visualizations. So that is our research background. And another thing about 3D geometry is that the morphing of 3D solid can be considered as spatially distributed. I don't know whether it's, oh, sorry. I think, playing? Yeah. So based on previous researches, the transformations of 3D solids can be converted into sort of like a map. So different stages of the transformations are visualized on the map, and those stages can be connected by lines, indicating a possible transition. So by converting those transformations onto a map, then we can have three types of basic knowledge on 3D geometries. The first one is landmark knowledge, which represents possible stages of a transformation, and it basically indicates how well users can understand the structural properties of a visualization. And also we can have route knowledge. It's like how the shape is transformed from one to another. And it indicates users' understanding of the transformational properties of the 3D visualizations. And finally, we have the survey knowledge, which basically involves the comprehension of the entire landscape. And that is how users are able to find out the potential connections between the multiple visualizations. So to further evaluate 3D geometries in VR, we developed interactive visualization tools in virtual reality environment that is supportive of the explorations of 3D geometries. And users are allowed to interact freely with those 3D geometric visualizations through the different interaction techniques we embedded, like grabbing, morphing the solids through a map, or just by moving one of its vertices. And one special about this tool is that no explicit guidelines were given on what to do next. Users are encouraged to interact and learn by themselves through observing clearly the consequences of a certain action. Yes. So that's the basic idea. And so we conducted an experiment to evaluate the tool. And the experiment can basically be divided into 6 phases. And 5 minutes to introduce the mathematical background to participants. And after that, participants were asked to complete a pretest. It's basically a questionnaire, consists of 18 questions regarding both landmark, root, and survey questions. And after that, participants spent 40 minutes to interact with our tool and complete some predefined tasks at the same time. And then participants spent 30 minutes to complete a it's named the Vis Engage questionnaire. It's designed in 2017 by Dr. Cousins from Purdue University. And it can visualize participants' engagement from 11 different categories, like here, statics activation, challenge control, and something like that. And the final result can be visualized through a bar chart on the right. And after that, we interview participants about their feelings when using the software. And also, participants are required to read on the interaction techniques we designed. And finally, participants spend another 20 minutes to do the post-test. It's like this has exactly the same question as a pre-test. So we are able to compare the result between the 2 tests to find if their knowledge are improved or not. For evaluation, we have both qualitative and quantitative measures. For quantitative measures, we have score improvement from pre-test to post-test. And we also have the engagement score and the Likert ratings on interaction techniques by participants. And we also have qualitative measures. It's like screen captures and video recording of the interactions and the transcripts of the interview and also participants' comments left on the questionnaire. So here is the result. Below are the box plot for pre-test and post-test. And the result shows that the test scores increased significantly by 20% from pre-test to post-test. And which basically means that interactive visualizations in VR can be supportive of explorations and analytical reasoning tasks. And also because we found some previous work saying that VR experience could vary among genders, so we also made a comparison on test improvement between males and female participants. And there was no significant difference between them, which means that the tool could be equally effective, regardless of genders. And also, all the 3 categories, landmark, root, and survey, just as I explained, they experience some level of improvement. And landmark is improved by 25%, and route is like 22%, and survey is improved by 12.5%. The higher improvement on landmark and route questions indicate that interactive visualizations in VR could be helpful on users' explorations on transformational and structural properties of 3D visualizations. However, it is also noteworthy that participants' improvement on survey questions is not as much as landmark and route questions. So let us pay a close look at the engagement chart we obtained from the Vis Engage questionnaire. For engagement level, our tool obtained 132 points out of 154. It's around 86% of the entire score, which is really high. And especially on the chart, the tool was rated high on novelty interest and also explorations and discovery categories. However, it can be noticed that the tool was rated low on attention category specifically, which is kind of consistent with the lower improvement on the survey questions, as both of them indicate their comprehension on multiple visualizations, the transformations of multiple visualizations. So here we can conclude that, and also based on the interview result, and participants are saying that they are finding hard to observe multiple visualizations at the same time. So for example, here in this picture, participants are interacting with the solid on the right. He cannot really see the other solid visualizations within his field of view because of the limited field of view of current head-mounted displays. So for the ratings on the interaction techniques, I'm sorry that I cannot explain all the techniques in detail due to limitation of time, but for more information, please refer to our paper. And here, what we found is that interactions techniques that cast interaction directly on the visualizations were more frequently used and received more positive comments from participants. For example, here we have two techniques on transforming the 3D solids, and users can interact on the map, or they can just move one vertex of the 3D solids. And then we found that participants used the technique on the right more frequently, and the technique obtained higher ratings as compared to the left one. So here we think that direct manipulations could be emphasized to promote positive visualization engagement as compared to indirect ones. So here I will list some limitations and future work of our research. The first one is definitely the lack of comparison with other platforms and displays. Because we are sort of indicating that VR could be helpful on exploring multiple visualizations, but we are not comparing the result with like a standard display or maybe like tablets or desktop PC devices. And that is the major limitation of our work. And actually we have already been doing that. And we are doing the data collection phase right now, and hopefully the result would be published soon. And also, we need to design proper techniques for interacting with multiple visualizations in VR, given this limited field of view. For this part, there are already some excellent work that has begun to address this common problem of head-mounted displays for this year's SMAR. And it's my belief that with the effort of our dedicated researchers, it would no longer be a problem in the near future. And also, the last but not least, our work indicates that participants would specifically favor direct manipulations on the visualizations, but it is not clear whether this is beneficial to the learning process or the explorations. So I think this can still benefit from further investigation. And that's all for my presentation. Thank you all for listening.
Thank you. Thank you. Are there any questions in the audience? A little bit tired. Of course, I have one. So regarding the generalizability of what you found, right? So you did that with these very specific mathematically, geometric objects. Mm-hmm. So could you give us examples of how generalizable it would be? Because it was one of your assumptions that it is generalizable.
Because when we are doing the literature review, we found that like far from the ancient time, 3D geometries are like being considered as important to comprehension of any 3D structures. And also, the testbed we are using 3D geometries has structural and transformational properties basically related to the structural information of 3D objects and how it is related to other ones. So I think in this case, it is generalizable to many visualizations that have such properties.
Okay, yes. Including things like design and architecture you had in your
yeah,
okay.
Yes, yeah, exactly.
Yeah, okay. Any other questions for speaker? No? Then let's thank him again, please. Thank you.